Okay. So this is a section on something near and dear to my heart, parametricity. We have 3 papers taking quite different views of parametricity. I attached a named parametricity theorems for free, which sort of lives on. So you can see it hiding in the title of this paper. And so I'm very interested to hear. So there's a standard result that goes back before parametricity, I think due to Knuth, that says if you test your sorter on just 0s and 1s and it always works, then it works for any numbers. And this is a descendant of that theorem, I think, which I'm very interested to hear about. So Kazuhiko is going to tell us all about it.
Thank you for the introduction, and hello, everyone. So I'm going to present my joint work with Cyril Cohen on functional correctness proofs of Mergesort. So more precisely, the contribution of this paper is modular correctness and stability proofs of several variations of Mergesort. Our approach applies to top-down, bottom-up, non-tail-recursive, tail-recursive, non-smooth, smooth Mergesorts, and even the ones in the standard libraries of OCaml and Haskell. The proofs are twofold. Firstly, we prove that each Mergesort function satisfies what we call the characteristic property of Mergesort. Secondly, we deduce the correctness results solely from the characteristic property, so the latter part of the proof is shared between several implementations. As the title of the paper implies, our proofs use relational parametricity. We formalized this proof technique in the Rocq Prover. I believe that our characterization and proofs give clear insight into what Mergesort does. So even if you don't do any verification work, I hope that this talk and the paper will help you in, first, better understanding Mergesort, second, getting your implementation of Mergesort right. Let's take a look at 2 examples of Mergesort, namely top-down and bottom-up Mergesorts. Top-down Mergesort is the one you often see in a textbook. Its idea is to, firstly, split the input into 2 halves, secondly, sort each half, lastly, merge them. The recursion stops when the input is singleton. The binary tree on the right depicts an example of top-down sorting process where a branch node represents merge. On the other hand, the idea of bottom-up Mergesort is to firstly split the input into singleton lists, secondly obtain sorted lists of length 2, then 4, then 8, and so on by merging the adjacent pairs, and lastly, eventually obtain one sorted list. The binary tree on the right depicts the bottom-up sorting process for the same input as before. We call these binary trees showing the divide and conquer structure of an execution of Mergesort traces. Indeed, these top-down and bottom-up traces have different shapes. It explains the fact that to verify several implementations of Mergesort, we need to verify some lemmas by induction for each implementation. Basically, eliminating this duplication is the motivation of this work. Before defining the characteristic property, let me give the intuition behind it. The intuition is that by replacing merge with concatenation, we can turn any Mergesort function into the identity function. If it is not the identity function, but may permute some items, the sorting function in question is unstable. We can easily check by functional induction that this claim holds for the top-down and bottom-up Mergesorts shown in the previous slides, which are in fact stable. In the next slide, I'm going to define and explain the stability and then justify our claim. A sort function is said to be stable if it preserves the order of equivalent items. Note that equivalent here does not mean equal because we do not assume the relation to be an order but a pre-order. To ensure the stability of our two examples, we were actually assuming that they use this implementation of merge. The crucial point is that when two items x and y being compared are equivalent, merge gives precedence to x, which is the head of the first list xs. So two lists xs and ys must correspond respectively to the former and latter part of the input. Therefore, if we replace this merge with concatenation, it should not permute any item. To put it in another way, let's instantiate the comparison function with the trivial preorder that always returns true. Then merge below becomes equivalent to concatenation. The predicate equiv x in the definition above becomes always true. And so filter by equiv x becomes the identity function. Therefore, sort s is equal to s. To sum up, this instantiation has the same effect as replacing merge with concatenation and turning the definition of stability into the one, saying that sort is the identity function. Now we define the characteristic property. A function sort of the first type on this slide satisfies the characteristic property if there is a corresponding abstract sort function a sort of the second type on this slide, such that it is sort when instantiated with merge. It is the identity function when instantiated with the concatenation, and it is relationally parametric, which I will describe in the next slide. This type variable R morally represents the type of sorted list, and both of the first two conditions below instantiated with list T. However, the use of parametric polymorphism on R is crucial in making sure that a sort builds sorted lists using only three operators, namely merge, singleton, and empty. In fact, this property is ensured by the third condition, parametricity of a sort. As I said, we need to prove the characteristic property for each merge sort function. Usually, the first and second conditions can be proved by functional induction, and the third function follows from the abstraction theorem, again, which I will describe in the next slide. If this sorting function in question is sufficiently simple, the first condition should hold by definition. And it is the case for the top-down and bottom-up merge sorts on the previous slides. Parametricity is a property of polymorphic functions that they cannot inspect the type variables, and so they should behave uniformly regardless of the type with which we instantiate them. We say that a term T of type A is relationally parametric if T is related to itself by the relation square bracket A. These square brackets interpret types as relations. For example, two functions f1 and f2 of type S to T are related if it's the first case, if they map terms related by square bracket S to terms related by square bracket T. And the second case says that two polymorphic types of type fall ST are related if for any types S1 and S2 and the relation on them, F1 S1 and F2 S2 are related by square bracket T, where this square bracket T interprets S as the given relation. The interpretation of ground types such as Booleans and natural numbers is just equality. The interpretation of polymorphic container types extend the given relation in a pointwise manner. For example, two lists of type list T are related if they have the same length and their items are pairwise related. Here I present a simplified version of an abstraction theorem, which says that closed terms in the empty context are parametric. In the rest of this talk, I described the second part of the proof, that is, how our characteristic property implies the functional correctness and stability of Mergesort. From the characteristic property, we derive two key properties. The first one is an induction principle over the traces of sort for reasoning about the relation between the input and output of sort. The proof of this lemma is just a straightforward application of the parametricity of A sort. We do so to show that the given relation relates the two instantiations of A sort that appear in the characterization, which I call to S and sort S. In fact, this induction principle, an instance of the general fact that parametricity implies induction principle on Church-encoded data types. As you can see, the type of A sort instantiated with concrete T and input is the type of Church-encoded binary trees. As an example of use of this induction principle, we prove that sort S is a permutation of S. For the induction case, we need to prove that whenever S prime and T prime are respectively permutations of S and T, the merger of S prime and T prime is a permutation of the concatenation of S and T. The base case follows from the reflexivity and the reflexivity of the permutation relation. Our induction principle also implies our first main theorem, namely sortedness and stability of sort. Here we assume that the input to be pairwise sorted with regard to relation 2, and then the result of sorting it by relation 1 is sorted with regard to the lexicographic composition of relations 1 and 2. While sorted means that any two adjacent items are related, pairwise sorted means that any two items that appear in order are related. In other words, the pairwise sortedness extends the sortedness with transitivity. While I'm not going to show the detailed proof of this main theorem, this is the key lemma for proving its induction case. In the proof of this main theorem, the second assumption of the lemma follows from the pairwise sortedness of the input, and the third assumption of the lemma follows from the induction hypothesis. The second key property we derive from the characteristic property is the naturality of sort, which says that sort commutes with map. Basically, this is a free theorem that follows from the parametricity of sort, which follows from parametricity of A sort. From the first main theorem and the naturality of sort, we derive our second main theorem, which says that filter commutes with sort. Here is a proof sketch in the backward reasoning style. Firstly, we replace S with map f S prime, where S prime is the list of indices of S, and F maps indices to items. Secondly, we move the application of map using the naturality of filter and sort. Here we change the relation and the predicate P with their preimage under F. That takes indices. Thirdly, we apply the congruence rule. To prove the last equation, it suffices to show that both thighs contains the same set of items and both thighs are sorted with regard to this strict order. Note that here we turn a non-strict preorder on indices into a strict order on indices by lexicographically composing the former with the strict less than relation on natural numbers. Indeed, we use the first main theorem to prove this sortedness condition. Stability can be seen as a corollary of our second main theorem because a list collecting equivalent items is a fixed point of sort. In contrast to this formulation of stability, our second main theorem applies to filter by any predicate P. In the paper, we argue that our main theorems are more general than this corollary. Let me briefly go through the rest of the paper before concluding this talk. In section 4, we extend the characteristic property to support tail-recursive merge sort, which requires tail-recursive merge, and smooth merge sort that reuses sorted slices in the input in the sorting process. In section 5, we explain technical aspects of our Rocq formalization. The first one is a technique to make merge sort structurally recursive so that Rocq does not ask us for a termination proof. The second one is the interface for stable merge sort function, which enables overloading of our correctness lemmas through so-called canonical structure. The third one is automation of parametricity proofs using the parametricity translation. In section 6, we discuss the limitations of this work. Most notably, we didn't find a way to prove the characteristic property for the merge sort function of recent GHC due to its merge function that takes 4 lists instead of 2 lists. Let me conclude this talk by abstracting out a merge sort function and re-instantiating it differently. We obtained the identity function. The characteristic property implies the 2 key properties of merge sort that are sufficient for proving the functional correctness and stability of merge sort. The first key property is the induction principle over the underlying binary trees or traces of sort that relates the input and output of sort. The second key property is the naturality of sort, which is a free theorem. That's all I have for you today, and I'm happy to answer your questions.
Okay, we've got a couple of mics available. So I'll ask a first question while people rush towards the mics. Can you go back to the slide where where you gave your stability theorem, the key theorem.
The definition of the stability, you mean?
The theorem, I think it was.
Theorem, stability as a theorem.
No, the one where you said if it's relational, the one where you gave the three properties that needed to be satisfied.
Okay, you mean the characteristic?
There you go, that one.
Okay, yes, this.
So there's something I'm slightly confused about, right? It says this will satisfy the CP if these three properties hold, and haha, I think I see part of it. So what I was worried about is you say it's relationally parametric, so that gives you things about all sorts of things, but then you were instantiating these, right? And a sort can satisfy those if it ignores its second and third arguments.
Sorry, say it again.
So it looks like we're saying, okay, the first argument is how you combine stuff. The second argument is what you do to make a unit list. And the third argument is what you do to make the empty list. But
yes.
Oh, I understand what's going on. So I thought, but you could just ignore, right? You could easily satisfy the first two properties by ignoring your second and third arguments.
The second and...
But you can't, in fact, satisfy by ignoring the second and third arguments because it's got to be polymorphic. So you couldn't instantiate the second, you couldn't just replace using the second and third arguments by the unit list function and by the empty list function, because if you did, they'd have the wrong type.
Right.
So, okay, yes. I answered my own question.
So basically, merge singleton empty are constructors of sorted lists here. So, and we wanted to make sure that this A sort builds sorted lists only using these three constructors.
Okay, and no other questions? You were too clear.
Maybe.
So you talked about this in general, and the general property is, of course, right, the whole point is it's very general, so it works for lots of things. But what's an instance of a useful theorem that you got out of this? Right, so a particular kind of merge sort has this property?
Not really. We just have general theory of merge sort that applies to any instance of this characteristic property, and I don't really have lemma about merge sort that is really specific to one implementation or one particular kind of implementation. I don't have any example.
Right, so the quicksort people made good use of the fact that, does next person want to come up and start getting ready? Are you going to do that? Good. So why don't you come up and, you don't want that bright light in your face? Go ahead. Good.
You're right. Yeah. Okay,
now you can.
Thanks for the talk. Maybe a naive question, but could you do this for other types of sorting algorithms?
Right. So this characteristic property also applies to insertion sort, like correctly implemented insertion sort that is stable, but we don't really have not only sorting algorithms, but we don't have any other kind of algorithm where our proof technique works. So that would be the honest answer. So we just don't know.
Okay, thank you.
In your formalization, do you rely on any axioms?
No, not at all. So for maybe one concern is the parametricity proof, right? So okay, should I So I actually have...
No, you have to unplug because he's going to plug in while you answer. Or do you have a slide that answers it?
So yes, so the thing, the thing is that, for parametricity proof, we use parametricity translation. So it takes a term and produces its witness of parametricity, represented as a Rocq term.
So you can do this because you work with closed types, so your proof is not parameterized over like any type with an ordering or something like this, but you work with some concrete types, right?
Yes, exactly.
So if it was more general, then you would need an axiom.
Yes, yes, I think so.
Yeah, thank you.
Okay, so where do you want me to...